Right, so today I will be talking about rate splitting multiple access, and in particular, how we can use rate splitting multiple access in satellite communications. So this is what I will be talking about. First, I will briefly introduce some issues in satellite communications, and then talk about multiple access techniques. Then I will jump into rate splitting multiple access, in short, RSMA, see how it works, what are the main building blocks. And then we will, instead of looking at application of RSMA in lots of different scenarios I usually give in various tutorials, in this talk I will focus on application of RSMA in purely in satellite communication. And I will talk about scenario where you have multi-beam communications, where you have multiple gateway, and when you have integrated satellite and terrestrial networks. And then we look at the physical layer design of RSMA, so the whole link level and link level simulations and application of that in satellite context. And then we will look at some, we'll draw some conclusions. Right, so satellite communication is not something that is new. People have been, studying satellite communication for quite a long time. And actually, I did my master thesis a long time ago on satellite communication. And then that was very popular in around 2000. And then it became a bit less popular. And I think nowadays it's becoming popular again. So there are three rules for satellite communication. The first one, reliability. The second one is frequency, and the third is scalability. Reliability provides service and this to somehow complement terrestrial networks that serves only have a limited coverage. Here we try to serve either unserved area or underserved areas. So those are areas that actually would be too costly to cover through a terrestrial network. And then you have the third role is scalability, which is the fact that you want the service to grow even if you have many users to serve, and this can be done through multicasting or broadcasting over a very wide area. Right, so what are the use cases for satellites? Well, you have use cases in urban area, in rural area, and in remote area, and I just give here some application or use cases coming from this tutorial paper here. So you have, for instance, IoT connectivity, you have fixed backhaul, you have broadcasting, you have connected cars, disaster relief, media broadcasting, backhauling in rural areas, connectivity directly to homes through VSAT, for instance, tracking of cars or vehicles, maritime, and M2M. This is more in remote areas, aeronautical broadband, and emergency safety. Lots of different applications. Right, so there are different types of satellites. So you all know about GEO, MEO, and LEO, and the difference is essentially the altitude. So GEO is really high in the skies at 36,000 kilometers high altitude. MEO is a bit lower, and LEO is very low. And then you have in the LEO, you have also the VLEO that really operate at even lower altitude. And so because they have different altitude, essentially the orbital period is very different. The GEO is stationary compared to the Earth. So essentially it turns around in the orbital period is 24 hours, while the LEO would take 10 to 40 minutes to fly around the Earth. So it's much faster. The GEO has a pretty long satellite life, while the LEO is relatively short. And then there is difference in terms of handover. There is no handover in GEO because they're stationary compared to a certain point on Earth, while the LEO, you need a lot of handover or handoff simply because they are moving very fast. And so nowadays, people are moving, not nowadays, it's been discussed for quite some time, that actually satellite frequency are going up. So already 20 years ago, people were talking about the use of Ka bands for satellite communication. And progressively, we've seen that the use of higher bands have been used or are planned to be used in satellite communications. So for instance, I think Ka would be used for downlink. I think Ku was uplink or something like this. Right, so modern, especially geosatellites, multi-beam satellite systems. And this is a representation of the basic architecture. So you have a gateway. You can imagine this as a kind of a base station. You have a satellite. Then you have here the terminals, the satellite or the user terminal. And so the uplink here between the gateway and the satellite is called the feeder link. The link between the satellite and the terminal is called the user link. And the concatenation of the feeder link and the user link is called the forward link, and the return is called the return link. And so in each spot here, you have here, this is actually formed by a beam. This circle is formed by a beam and a satellite. And so you have multiple of those spots, multiple of those beams. And in each beams, you have multiple users that are served simultaneously. Right, so what are the challenges? The first challenge is to move away from high frequency reuse. Frequency reuse has been used quite a bit in satellite communication. And if you move away from high frequency reuse and you try to aim at frequency reuse of 1, then you have higher level of interference. That's the first issue. The second issue in modern communication systems standard, and this is something that may change in the future, but at least currently, if you look at the DVB-S2X standard, the way the transmission operates is that it's frame-based recording. So that means that in a given beam, if you want to serve multiple users, the packets of all those different users will be encoded into one code word that's going to have to be decoded by all the users. And so you can view here in this, you're going to have one code word that will have to be decoded by all the users within that beam, another code word that's going to be decoded by all the users within that beam here. And so effectively what the system looks like here on the user link from the satellite to Earth, it looks like a multi-group multicast problem, where in each group you have essentially multiple users, and each group here is represented by effectively a beam, one beam. So we will come back to this, and so we'll see how we can actually relate multi-group multicast to satellite communication. Another issue is the power constraints. So you have a per feed power constraint because the power sharing among power amplifiers among the antenna elements is very complicated, obviously. People in satellite are extremely cautious about the effective use or efficient use of power. And so here we don't play with a total power constraints, but more with a per feed power constraint. So you can relate this in terrestrial, that would be, for instance, the per antenna power constraint. And then the satellite channel is different from what we have in terrestrial. It's more dominated by line of sight. And it has another component that is the atmospheric fading that may come from, for instance, attenuation due to oxygen and various gas absorption. As well as, for instance, rain, or you can have scintillations or things like that. And then the last thing is the knowledge of the channel state information on the satellite link could be different from terrestrial, and that may depend on what type of satellite we assume. For instance, if you have a geo satellite, there is a very long latency to feed back any CSI. On the other hand, the satellite is geostationary, so the channel does not change that quickly. On the other hand, if you take a LEO satellite, maybe your latency is lower, but the satellite moves extremely fast. So this imperfect CSI needs to be modeled as well and captured in the design. So looking at multiple access techniques, existing ones. So we have this very maybe naive representation of multiple access. On one hand, you have the orthogonality. On the other hand, you have non-orthogonality. And OMA stands for orthogonal multiple access. You're all familiar with this. You have example of TDMA, FDMA, or FDMA. So essentially, you split resources into orthogonal orthogonal slots, and on each resource or each slot you have one user is assigned, and so you don't have any multi-user interference there because essentially the scheme has really eliminated any form of multi-user interference. Then you have SDMA, which is essentially making use of the spatial domain to pair users, so multiplex users. And so here you use typically linear precoding or multi-user linear precoding to separate users in the spatial domain. And this is probably the most popular multiple access techniques that has been used extensively in 4G and 5G, in multi-user MIMO, massive MIMO, millimeter wave, and network MIMO, for instance. All right, so the way it works is actually your base station here, or you can think of in satellite context, you may have your satellite create beams like this, and you try to serve one user per beams as much as possible. And those beams are adjusted depending on the channel state information. The important bit is what you do at the receiver is that anytime you have any residual interference, you simply treat it as noise. And so the architecture looks like this. You still K users. You have K message delivered to those K users, one message per users. You encode them into K independent streams. You precode them, you transmit over the air, and then each of those users will decode his own stream by treating any residual interference response. So the important bit, and I will come back to this later on, is really fully treating interference as noise. So that's the important bit here. So the benefit of SDMA is it's actually a very simple strategy, or relatively simple. So it has low precoder and low receiver complexity, and it enables you, nevertheless, to reap all the multiplexing gain or all the degrees of freedom that you have in a multi-antenna, multi-user communication when you have perfect CSIT. The drawback of this kind of strategy is that it doesn't work as well when the system becomes overloaded. So when you start having to serve more users than the number of antennas that you have, it can be problematic. And this is something that can happen in a satellite context. It works well when the channels, the different users are semi-orthogonal to orthogonal, less when there is a disparity of channel strength or whenever the channels are a bit more aligned. And importantly, is not very robust to imperfect knowledge of the channels that it transmit. This is something we have seen extensively in 4G and 5G. If you take multi-user MIMO and massive MIMO in 4G and 5G, it's very depending on the quality of the CSI. So whenever you have a bit of mobility, the performance can drop quite significantly. Or if you have imperfect channel state information or estimation or quantization, the performance can drop. And as I said earlier on, you treat any residual interference. Now, NOMA, on the other hand, is been advertised as a non-orthogonal multiple access. And also here you use the power domain to break the orthogonality using superposition coding and successive interference cancellation. And the way it works is the following here. So you have a transmitter that wants to deliver two messages, one message to user 1 here and one message to user 2. And the way this is done is by superposing those two messages that have been encoded into code word. You superimpose them in the power domain. You allocate a certain power to user 2, a certain power to user 1. And the way the system works, the way the power is allocated is such that at the receiver, one of the two users, typically the strong users, the one that has a better channels, decode the message of the weaker user. So in this case here, user 1 is closer to the base station, has a better channels than user 2. So user 1 will decode the message of user 2 and then perform successive interference cancellation and decode his own message. This is what you see here. He receives both messages. He first decodes the red one, the one intended for user 2. He peels this off and then decode his own message, his own stream here, the one that is intended to user 1. On the other hand, user 2, what he does, he sees the two message coming to his receiver and actually will treat the message of the user 1. He will treat this as noise and he will fully decode his own message by treating the message of user 1 as noise. So you see the two receivers are quite different. This one treats interference as noise, while this one, what it does, it fully decodes interference. The strong user fully decodes the message of the other user. So this strategy is well known for several decades, but has been revisited in the recent year and especially in standardization. I think a study item was introduced on that, but I'm not sure there was a work item in 5G because the gains were not shown to be convincing enough, at least the downlink. So the important bit I want to emphasize here is the fact that in NOMA, you have a user that fully decodes the message of the other users. This is completely different from what we had in SDMA. Right, so now you can apply NOMA in a multi-antenna context. And so for instance, here you have a transmitter with multiple antennas, and then you can create different groups. And in each group, you have multiple users. And the key principles here is that in each of those groups, you have one of the user, for instance, here user 1 will decode the message of all the other users. So this is the key basic principle of what you have in this multi-antenna or power domain NOMA schemes. And we have to be very careful here. We have to be careful because by doing so, you can have an inefficient use of the multi-antenna on one hand, and you can have an inefficient use of the SIC receiver on the other hand. This is something that we have tried to emphasize in a recent paper here with many of my co-authors about being very cautious when we try to combine multi-antenna techniques and non-orthogonal multiple access. So what the main observation is the following one. NOMA, we know its capacity achieving when you have single antenna broadcast channels, when you have single antenna nodes. So one antenna at the transmitter and one antenna at each of the receiver. And this works really well when you have a diversity of channel strength among users. The drawback is that actually is not motivated at all by multi-antenna broadcast channels. Once you have a multi-antenna, multi-user communications, we can show quite easily that this is not a good strategy in terms of coming close to the capacity region. And the reason for this is actually it can decrease quite significantly the multiplexing gain or the degrees of freedom of the network. So it can work in some specific settings when you have aligned users. So when you have the channels of two users are very aligned with each other, that works well. But that's not something that you can expect in typical multi-user, multi-antenna deployment. And the issue with this is that you have a complexity increase. So you have a DAF loss that comes on top of the complexity increase at the receiver, because now you may need multiple SIC at the receiver to cancel the interference. So in terms of property, the key is to understand that what NOMA does is actually trying to fully decode and cancel interference. This is a completely different extreme to the one we have here in SDMA, where we treat any interference as noise. And so if we go to rate splitting multiple access, what we have here is something that is based on what is called rate splitting techniques, that I will explain in a minute. And this rate split multiple access is a general, flexible, and robust multiple access. So it's general because we'll show that actually it incorporates, or actually it subsumes SDMA, NORMA, OMA as special cases of these multiple access schemes. It's flexible because it does not restrict itself to actually be in a regime where interference is treated as noise, or in a regime where interference is fully decoded. It can bridge the two extremes of treating interference as noise and fully decoded, and in a way, therefore, bridge SDMA and NORMA. And it's robust because it's robust to imperfect knowledge of the CSI transmitter. And this has been shown, we have shown this, that it's actually optimal, information theoretically optimal from a degrees of freedom perspective. And so the idea of this RSMA builds upon the concept of rate splitting that was introduced for the two-user single antenna interference channel 40 years ago by Carlyle and Hanen Bayashi, and is being exploited in different settings here. First, when you have multi-antenna, but second, and mainly when you have a broadcast channel. So when you have one transmitter serving multiple users. So this is what we're going to really exploit here today. Now, the key is really this rate splitting. What it enables to partially treat interference as noise and partially decode it. And by adjusting this part, those two parts, we can really bridge SDMA on one hand and NORMA on the other hand. Right, so how does it work this is the simplest example of RSMA for a two-user setting. So you have, on the left here, you want to schedule two users. So you want to transmit two messages to two users, one message per user. So W1 is a unicast message intended to user one, and W2 is another unicast message intended to user two. And we have here two users, user one here, and you use user two here. Oops, sorry. And what we have is the way you would do it if you do SDMA is the following. In SDMA, you would take W1, if we go back to this figure that we had here, you would take W1, you would encode this into a stream S1, and you would take your W2, you would encode into a stream S2, and linear precode them and transmit over the air. Here, what we do is we don't do that. Before encoding any streams, we take those two messages and we split them into two parts. My message W1, I split them into two parts, WC1, WP1, and W2 is split into two parts as well, WC2, WP2. And this is what we see here. We have the blue part of the bits goes here, and part of the bits goes there. And similarly for the red part of the bit goes here, part of the bits goes there. Then I take those parts here, this common part W1, and I combine them into a new message I create. It's called WC. And now I have three messages, WC, WP1, WP2, and I code them independently into three streams, SC, S1, S2. SC is what we call common stream, S1 and S2 are called private streams. And so what you see here is that you start from two messages, W1, W2, and you actually from this create three streams, SC, S1, and S2. SC can encode part of the bits of W1 and part of the bits of W2, while S1 and S2 encodes bits from W1 exclusively and from W2 exclusively. And then we linear precode them. So we take SC, we precode by PC, S1 by P1, S2 by P2. And then what do we do? Well, the receiver, both users first decode this common stream SC. So both receiver will operate in the same way. I don't display the user two receiver here, so we just look at user one, but you have both receiver will first try to decode SC. And so here you have actually an estimate of SC that you decode into this common message here, WC. So you get an estimate of your common message, WC. And what user one does is actually he retrieve from WC, he retrieve the blue part. The blue part was the part indeed intended to user one. And then re-encodes WC into common stream, perform SIC, and then try to retrieve the message encoded into S1 into WP1 hat. And so because W1 was split into two parts, essentially user one at the receiver has to retrieve those two parts before recombining into the original message. This is what we see here. User one retrieve WC1, retrieve WP1, and then recombine those two into the original message. So when we do this, so both receiver decode the common streams, when then each receiver will decode his respective private stream. So user one will decode S1 by treating interference from S2 as noise, and user two will decode S2 by treating interference from S1 as noise. And so this is called rate splitting because the rate of a given user has been split and has been split into two parts. We have the rate of user one will be the rate of its private stream S1 plus part of the rate of the common stream. So the common streams, part of the bits encoded into the common stream carries information for user one. So part of the rate of the common streams is also intended to user one. So the sum of the rate of this part and the sum of, and the rate of the common, the private streams, the sum of those two will give you the rate for user one. Right, so where is SDMA and NOMA in this architecture? Well, if you do not allocate any power to the common stream here, you turn off this. That means actually you will not split the message, and W1 will flow directly into S1 and W2 directly into S2. What you end up with is P1S1 plus P2S2, and this is SDMA, or multi-user linear precoding, classical multi-user MIMO. So this is obtained as a subset of this architecture, right? When you simply turn off PCSC, so you do not allocate any power to these common streams. Where is NOMA? Well, NOMA is different because if you remember what we were talking about here, we were saying, if I'm user one will decode the message of user two, right? So user one is a strong user, he will decode fully the message of user two. So what that means is that the message of user two will be decoded by both users. The message of user two will be decoded by user one, but obviously will also be decoded by his own user, by user two. So the message of user two is decoded by both. So how can we do this with rate splitting? Is by saying, if I want W2 to be decoded by both users, what I can do is I can take W2 and encode W2, the entire message W2 I can put into the common stream SC. So what I do in NOMA, I take W2 and I encode into SC. I take W1, I encode it to S1. This is what we have here. W1 goes into S1, W2 goes into SC. And so what you do after you linear precode, you have PCSC plus P1S1. So you see this expression and this one, this seems the same because you have every time two streams and each stream is precoded, but actually it's quite different because in this case, S1 carries W1, here S2 carries W2, while here there is no S1, there is no S2, there is no private stream for user 2. But there is a common stream, there is a common stream that carries the message for user 2. And this common stream is decoded by both users, and so both users will decode the message of user 2, right? Now, with rate splitting, you don't do any of those extremes. So those are two particular cases, but in general, you can split W1 and W2 the way you like to maximize certain objective function. And the split will depend and will vary as a function of the channel realization, as a function of the objective function. And it may happen that in some circumstances, essentially the scheme boils down to this. In some other circumstances, maybe it may boil down to this. But in general, it may be something that actually is not any of those two extremes. So one clarification on this notion of common stream versus multicast stream. So some people sometimes can be confused about the common streams. So here is common stream means is really a stream that is being created for interference management purposes and is decoded by both users, but does not necessarily contain information for both users. So that means that I may have, for instance, in some scenarios, I may not split the message of user 1, or I may not split the message of user 2. I may split only one of those 2 messages, for instance. But is not the same as a multicast streams in the sense that it's not a message that is generally intended to both users. It's a message that is a stream that has to be decoded by both users for interference management perspective, but the content of that stream is not necessarily intended to both users, which is a difference with a multicast streams. Right, so in NORMA, even though it's not expressed this way, but NORMA also has a common streams because this SC carries a W2, carries the message for user 2. And so effectively SC is a common stream that is decoded by both users, but in this case contain information for only one user. W2 is intended only for user 2, but nevertheless, this common stream is decoded by both users. So this quantity here is really a common stream in the context of NORMA. Right, so a different way of seeing this is the following. Essentially, you have 3 streams, and the question is how you map your message to those streams. You have 2 messages, and you have 3 streams. And how you map them? Well, you put W1, W2 into S1, S2 into SDMA, and any interference between those 2 streams is treated as noise. In NORMA, you put your message of the strong user to S1, to a private stream. The message of the weaker user, you put into the common streams. If you do OMA, you still only one user, so you transmit either W1 or W2. For instance, here W1, and you transmit into S1. If you do rate splitting, you split your messages so that part of it goes into S1, part of it goes into SC, part of it goes into S2, part of it goes into SC, and you adjust how many bits you want to put in those 3 streams so that you can really bridge the 2 extremes of SDMA and NORMA, and ultimately get multiple access that encompass SDMA, OMA, NORMA, and multicast as special cases. So you can argue multicast is the case where you put all your messages into these common streams. It's all the users decode that common streams and decode the message from there. Right, so if you have K users, you can extend that. Now you have K streams, K messages here. And for those K messages, you create K+1 streams. So you end up with K private streams here that are linear precoded plus 1 common stream that comes from the split of those K messages. And so you have the parts of those unicast messages here that they've been encoded into these common streams. And you can adjust how much you split each of those messages. Right, so what we have shown, and I will skip all those parts, but what we have shown is with rate splitting multiple access is essentially you make use of the spatial domain and the power domain jointly using a linearly precoded rate splitting. And that enables you to partially decode interference, partially treat interference as noise, because you really adjust what you put in those 2 private streams where any interference is treated as noise, and what you put into the common stream here that is fully decoded by those 2 users. So by adjusting the content here and the power to each of those streams, you can really adjust how much interference is treated as noise and how much is decoded. And so that enables you to bridge the extreme of NORMA and SDMA, and consequently you have a rate of rate splitting that is always higher than SDMA NORMA, because SDMA NORMA are here subset of rate splitting. The interesting bit is that it's optimal from a degrees of freedom or from a multiplex gain perspective. So multiplex gain, for those who are not familiar, is the slope of the rate at high SNR. So it's optimal in perfect CSIT. That's not not really surprising, but in what is more interesting is that it's optimal in imperfect CSIT. So that gives you really strong confidence that actually this is a good scheme to go for, because it has a strong theoretical foundation to be robust to all form of CSIT. So what we have been able to show is actually then, because of this flexibility, it can cope with any user deployment, so diversity of channel strength and direction, CSIT and accuracy and network load. And you can have a lower complexity than norma while having performance gain. This is one that is highlighted here. For instance, in this architecture, you transmit K messages, but each of those receivers only needs one SIC. So this is a particular instance of a rate splitting architecture that requires only one SIC at the receiver, but so has relatively low receiver complexity, but nevertheless can give you quite significant performance enhancement, and can give you a performance enhancement over NORMA schemes that have many more SIC receivers. And the reason for that is, again, because we do not force ourselves to be in a decode interference regime or actually treat interference as noise. We can adjust and be in this gray area in between. And the drawback is that you have a higher encoding complexity. And so in this architecture here, instead of having K streams, so instead of encoding K messages into K streams that you would do in SDMA, for instance, now you have to encode this into K+1 stream, so you have one more stream to encode. So that could lead to a slightly higher encoding complexity. Right, so now that we understand that, how can we use this in satellites? So in satellites, we have multiple challenges to consider. First, CSIT uncertainty. Second, this frame-based processing, and the fact that we can have overloaded regimes. So we may need to serve more users than the number of antennas or beams that we have at the satellite. We can have a very uneven user distributions or hotspots. So you can have beams that actually are very crowded and beams that actually are very almost empty. And you have a power budget that is a per feed, that has a per feed transmit power constraint. So the way we model this is the following. So you have K users that are served by M multicast satellite beams. So you have here in this figure that I had earlier on. So imagine you have K users. Here you have K users. Here you have 6 beams in this example. Let's say you have 20 users. And so in each of those groups, or each of those beams, you may have multiple of those users. And because of this frame-based processing, the message of each of those users would have to be encoded into one common code word before being pre-coded and transmitted over the air. So this is really a multi-group, multicast problem. And so mathematically, how we can formulate that is the following here. We have n multicast beams. So we essentially encode the message of those users in a given beam would be encoded into a certain private stream SM for the beam M, for instance, and part of that information for users in that beam may be also encoded into the common stream SC. So here you see that instead of transmitting across simply M beams and having each beam transmitting message for a subset of users, what we do is that the messages are split. And so part of the message of a given user will be encoded into the common stream and part of it will be encoded into the private streams. And so what we have to do here is to optimize the common precoders and the private precoder. And to do that, we have to define what is the rate for the beam M, so the private beam, and the rate of the common part. And so you have here the rate of a given beam will be, and I'm looking here, we will look at maximizing the minimum rate among all the users. So what I'm looking here is the rate, I'm looking at the minimum rate of all the users within a certain beam. So G of M refers to all the users within beam M. And I'm looking at the minimum rate of all the users within that beam, M. And so I want to maximize this. This is would be the rate of my private part. And then on top of this, I'm having a common part that has to be decoded by all the users in the network. And so to do that, I need to transmit a common stream at a rate that is given by this, that is equal to a minimum among something here. So what that means is that you have k users in the network, and you want to transmit the common streams that is decoded by all those k users. So you have to transmit at a rate supportable by those k users channels, and this is where the minimum comes from. Okay, so you see here the rate splitting again coming in, because part of the rate comes from the common stream and part of the rate will come from the private streams. And what we do is that we maximize the minimum among all the users or among all the beams of the rate of that beam. So essentially what that tells us is that you try to maximize the minimum rate among all the users. So this is the rate that you have for a given beam. This is the constraint that you have for the decodability of the common streams. This is the power constraint coming from the per feed power constraint. And you have the fact that the portion of the rate that is allocated towards the beam M has to be positive. And so you can solve this problem. Typically, this is done using WMMSE methodology and alternating optimization. And if you have imperfect channel state information, then depending on the model of the CSIT imperfection, then you can adjust the whole optimization frameworks. If you're interested, you can refer to those papers here. So what we obtain with this is the following. So this is an example of, we have 7 beams and 14 users. We have 2 users per beam here. That's denoted here. So each beam has 2 users. So it's quite uniformly distributed. And you have rate splitting and no rate splitting. No rate splitting refers here to classical multi-user linear precoding. So there is no split of the message. And you see that, for instance, in perfect CSIT, blue one is multi-user linear precoding and red one is rate splitting. And so that gain here, that translates into quite a big gain in terms of saving per antenna feed power. You see that you can decrease by what, by 60 watts. So you go from 120 here to less than 60 watts. So you decrease by a factor of 2 the amount of power that you need to achieve the same rate. And the reason for that is because the split of the messages enables you to manage the interference between all those beams much more effectively. If you have imperfect CSIT, you have the dashed lines, but the baseline, the message is the same. Essentially, the red curves are always significantly higher than the blue curves. So because of here, you have the double benefit of managing the interference between the beams and also being more robust to the imperfect CSIT. Then the baseline is the green curves, which are the frequency reuse. So we have a frequency reuse factor 4 here. So we have 4 color schemes. So all those different beams have different color, different frequencies that reduce the interference you have in the network, but that decrease the whole rate as well, because the loss due to the frequency reuse. If you look at the effect of the CSIT imperfection, as you go on the x-axis here from left to right, you actually degrade the quality of the CSI. And so what you see is that as the CSI quality degrades, relatively speaking, the gain of rate splitting over no rate splitting actually is increasing. And that's because of the robustness of rate splitting, the presence of imperfect CSIT. Right, here another example, if you have a per antenna feed power constraint compared to the total power constraint, what you see here is that the gray line is when you have a total power constraint, the dashed line is when you have a per antenna power constraint. Actually, if you do a proper optimization, the loss you incur by a per feed power constraint is quite marginal. So that's really not a significant issue, actually. If we go to a hotspot scenario, so here's a scenario, for instance, where I have 7 beams, 14 users, but instead of having 2 users per beams, I now have 8 users in the central beam and 1 user in all the other 6 beams. And so this leads to actually a complete imbalance between the rate in one beam versus the rate in other beams. And nevertheless, what we show here is, for instance, the pink one is rate splitting in this hotspot with perfect CSIT. The green one is when you don't do rate splitting in the same scenario, perfect CSIT in hotspot. And you see again here, the big saving you have in terms of per antenna feed power to achieve a given minimum rate. Right, so this was for a scenario where we have one gateway, one satellite, and then multi-beam scenario. The issue with that scenario is that if you want to serve more users, let me take a picture of the satellite. So we had a scenario here when we had one gateway, one satellite, multiple beams. And so if you want to increase the rate here, all the data that comes on the user link have to be also transferred on the feeder link. So you need to make sure that actually the throughput on the feeder link, or the capacity of the feeder link, is strong enough to to support all the data rate on the user link. And so what people have been looking at is how you can use multiple gateways to try to enhance the capacity here of the feeder link. And so the way it works is as follows here. This is what we have in our next work here, is how can we use rate splitting in a multi-beam scenario, but now when we have multi-gateway. So we have a satellite here. We have multiple gateways on the left side, and we have multiple beams here on the right side, and each beam, and beams have been clustered into clusters of beams. Beam cluster 1, beam cluster L, beam cluster capital L. And so we have different gateway, and the different gateway use the same feeder link spectrum. So the feeder link spectrum is reused across gateway, but those gateways have very directive antennas that aim towards the satellite. And so hopefully they will not interfere with each other, hopefully. In practice, of course, they always, to some extent, interfere. This is one of the challenges. And now each gateway can actually relate to a certain number of feeds on the satellites. We have a certain number of feeds, and those number of feeds here are divided into clusters, cluster 1 here, cluster L, cluster capital L, and this cluster of feeds is used to actually relay the data that is transmitted by the gateway L, essentially. And we'll relay that all the way to the beam cluster L. And so what you have in this scenario is that you have two issues. You have the inter-beam interference that you would still have, as we had in the previous work. So the interference between beam 1, beam 2, beam B1 here will still be there. You will have interference between clusters as well. But also you will have interference here between gateways, because the data transmitted by gateway 1 will leak into the feeder link of receiver of gateway L, for instance, and therefore will be transmitted and leak into the other beams. So you have the inter-gateway interference and the inter-beam interference to be managed. And so here you have a feeder link receiver that can be designed. And so the whole point is to use rate splitting architecture at each of those gateway that will split the message into common and private part that will be transmitted over the air. There will be a receiver here that will try to filter the interference coming from the feeder links, try to get rid of part of the interference coming from gateway L, gateway capital L, and so on. And then those rate splitting messages will then be amplified and transmitted over the air on the user link down into this beam cluster 1. And so this is the architecture that we have at each of those gateways. This is actually the rate splitting. So we have a certain number of messages here for users in a certain cluster. For instance, here I have a certain number of users here. Each of those users actually served by different beams. And so I'll take all those messages, and all those messages will be split into common and private parts and encoded by the gateway into common and private parts using this rate splitting architecture, the same one as the one I showed you earlier on. And then we have at each receiver will decode this common part, the private part, and then we'll try to recombine the original message. And so what we have here is a scenario where now we have 9 beams. Here you see 9 beams. We have 18 users. We have 2, for instance, you can have 2 users per beam, for instance. But then we have 3 gateways. So what that means, you have 3 different colors here. That means that this is actually handled by 1 gateway. This is another gateway. And the pink one is another gateway. So each gateway will perform its own rate splitting for all the users that actually belonging to all the beams served by that gateway. And then we're going to have another rate splitting for the yellow part, the yellow gateway, and another rate splitting for the pink gateway. And so obviously what we have here, we have still interference between beams, even within the same gateway. And we have interference between gateway as well that needs to be handled. And so what we do is that we do the optimization of the rate splitting jointly with what is called onboard processing, which is essentially the filter that is applied at each of those feeder link receiver here. And what we show is that if you can do a joint design of the onboard processing and the rate splitting, you can have quite significant gain. And this is what you see here. For instance, you have the pink one comes from the rate splitting combined with onboard processing, and the green one is just doing SDMA with onboard processing. And so this is the gain that you obtain. And this gain comes from the fact that the onboard processing is there to try to mitigate the inter-gateway interference as much as possible. And then you have the rate splitting behind that leverage that to further minimize or manage the interference between the different beams. Right, and so you can see this similarly to the previous scenario. You can do this with different in hotspot scenarios. So the observation here is the same. Even if you have an asymmetric distribution of user, you can still have significant gain by using rate splitting combined with onboard processing compared to using classical SDMA kind of techniques or no onboard processing. If you have, and as you increase the number of users per beams, then the rate will decrease. That is quite logical, so nothing very surprising here. Right, and you can continue, you can increase the number of beams, you can increase the number of gateway, the observation here is the same. So you see here you have, for instance, 7 gateways, you have 21 beams, so you have interference between those 7 gateways and among those 21 beams. And the combination of rate splitting and OBP, the pink one here, is what gives you the best performance over all other baselines that rely on essentially SDMA or schemes without OBP. The next scenario is when you have integrated networks, so satellite, terrestrial integrated networks. So this is a scenario where we have a multi-beam multicast transmission from a satellite, and you see this here, for instance, where you have multiple beams, and in each beam you have multiple satellite users. And then on top of this, you have within the coverage area of these beams, you have also satellite terrestrial network. And so you have some users here, they will be served by the terrestrial network. Some user here will be served by the satellite network. But those phone here, those cellular users could also be helped by the satellite network. And so if you have the same frequency reuse for the satellite and the terrestrial network, you have an interference problem to manage. Either you're going to have interference, those users here will see interference from the satellite, or depending on the way you design the system, you could actually, those users could benefit from the presence of the satellite, because the terrestrial antennas and the multi-beam satellite could jointly process information so that the terrestrial users benefit from that. Right, so how can we look at that? We have 3 problems to manage. We have the interbeam interference, that's the same as before. We have now the intracell interference, which is the interference within the terrestrial network, the interference here within the terrestrial network. So the interbeam interference, intracell interference, and then we have potentially the interference between the satellite and the terrestrials. So 3 types of interference to manage. And so we can come up with 2 different architecture, the coordinated schemes and the cooperative scheme, which is reminiscent of what we have in COMP, for those who are familiar. So the coordinate schemes is when you share the CSI to a gateway. So the CSI of those cellular users and the CSI of those satellite users are shared to gateway, and the gateway will design the architecture, will design, for instance, the rate splitting or the SDMA on the satellite sites, on the terrestrial site, but jointly such that there is we can minimize the interference between satellite and terrestrial. Or you could have a cooperative scheme that is more reminiscent of joint transmission in COMP, where you have CSI sharing and data sharing. And there you can design a joint rate splitting architecture that spans the satellite antennas and the terrestrial antennas in order to serve all those different users. Right, and this is the performance that you get when you optimize this system. You have, again, the MMF rate, so you maximize the minimum rate among all the users. So here, all the terrestrial users and the satellite users, all the cellular users and satellite users. And you have the full lines obtained by the coordinated schemes using rate splitting. That means that you do rate splitting on the satellite sites and the base station sites, so cellular sites, but only the CSI is shared among those different nodes, versus you do a joint rate splitting across all the antennas, across all the beams and all the antennas on the terrestrial base stations in a cooperative manner. And so what you see here is that as you increase here the power of the satellite, you see that the performance increases. That's the same here, whether you have coordinated or cooperative. As you go up here, you increase the satellite power. So all the minimum rate is increased. As you increase the power of the terrestrial base station, you have also an increase in the rate. And you see that at some point for a given satellite power, for instance, for 120 watts, we have those 2 curves here, the purple and the yellow. If you have a low power for the cellular base station, then you can have actually a relatively large gap between doing coordination and cooperation. But if your power level at the terrestrial base station is sufficiently large compared to compared to the satellite power, then at some point, coordination and cooperation gives you the same performance benefits. Here, in this regime, you see that the terrestrial user, the cellular user are kind of impacted because the SINR is actually quite small. While in this regime, the power of the base station has been increased, and so the SINR of the terrestrial users, the cellular user has been increased, and so it comes very close to what you can obtain from a cooperative scheme. So that enables you to tell you when you can have benefits from cooperation versus doing a simpler coordination. And this figure here tells you what's the benefit when you do coordination, whether you do RSMA, RSMA. So that means actually you do RSMA at the satellite and RSMA at the base station, at the terrestrial sites, or you do RSMA at the satellite and SDMA at the cellular base stations, or you do SDMA at the satellite and RSMA at the cellular base station, or you do SDMA across the network. And so you have different performance benefits. The more you do RSMA, the higher the performance gain. But you can see, for instance, the red curve here is higher than the yellow one. So the red curve is when you do RSMA at the satellite, but SDMA at the terrestrial base station is higher than the yellow one, which is the opposite, where you do SDMA at the satellite and RSMA at the terrestrial base station. So that tells you that doing RSMA at the satellite is actually more beneficial than doing RSMA at the terrestrial base station. And the reason for this is this interbeam interference. And that may depend on the number of users you have, but typically in the satellite context, you have higher interference among those beams than what you can have when you transmit unicast messages to, from terrestrial base stations. Right, similar observation here, so we'll skip that. Essentially, this is, it tells you how things change as a function of the number of antennas at the terrestrial base station as you increase from 4 to 64, for instance. As you increase the number of antennas at the terrestrial base station, essentially what it tells you is that you can use power level at the terrestrial base station actually are lower. But the whole observation that I highlighted before is still there. Then you have the imperfect CSIT in this integrated network. And the imperfect CSIT here is modeled using a phase. So you have a certain imperfection on the phase of your channel state information from the satellite link. And what you see here is that as your CSIT quality degrades, you go down here. So you go from red to green, your CSIT quality degrades. And this is for cooperation schemes. This is for the coordinated schemes. You see that in both cases, you have a drop in the performance. And this is when we do rate splitting. So we don't have here in that. This is rate splitting on the left side and SDMA on the right side. So you see the curves here are much higher than what you have on the right side, showing that essentially the rate splitting is more robust to the imperfect knowledge of the CSI, the transmitter. Right, so once we have this and we know how to optimize the system, then we can design the physical layer. And so an example of the physical layer here, in the two-user case, you have two messages that you split into common and private parts. And so you have to split those bits between the common parts and the private parts. Then you have to encode them. So here, for instance, we use polar codes for the common parts and the private parts. Different rate of the polar codes, and depending on the block lengths that we have for each of those common stream and private streams, that we have the interleaver, and then we have the adaptive modulation that can vary between QPSK and 256 QAM. And then we have the split of the messages and the rate of the common part and the private part, and the power allocation to all of them is obtained from the CSI that is acquired at the transmitter and from the optimization. And then we have the receiver that implements the receiver that I explained before, but here using really polar decoding. And so once you design this, you end up with a system that you cannot directly model using log2 1 plus SINR because you don't have infinite block lengths and you don't have Gaussian signaling anymore. So you need to come up with a kind of link adaptation to try to adjust your modulation and coding rates that you assume Gaussian signaling when you do your optimization, but then you have to adjust a little bit because you don't actually have infinite block lengths and perfect Gaussian signaling, you have finite constellation. But if you do that, then you can contrast the performance that you have for RSMA, SDMA, and NORMA using Shannon bound and capacity and the rate optimization. So that's assuming log to 1% versus actual throughput that you obtain when you do the actual link level simulations, when you have finite block lengths, when you have error propagation in the SIC, and so on. And you see that this gap here comes from the finite block lengths of the polar codes. But in general, the gain that you observe of RSMA over SDMA and NORMA, the gain from the Shannon bound or from the optimization is actually further increased when you look at link level simulation. And the reason for this is because here you now go from 2 messages to 3 streams. And so you can balance the rate of each stream more efficiently compared to the SDMA and the NORMA here that more quickly saturates because maybe one of the streams actually reach the highest modulation order, for instance. So that's the reason why here you have a gap that actually is further increased compared to the gap you have in Shannon bound. So this was for a 2 users, simplest 2 user scenario. Now you can apply this to a satellite context where you have exactly the scenario that I showed you earlier on, where you have those K, or G beams here, and you have multiple users in each of those beams. And so instead of doing the instead of having the Gaussian signaling and the infinite block lengths, you actually now run the link level simulations on a satellite setup with 7 beams and K14 users, and you can again contrast the performance you get with Shannon bound versus the one you obtain from the link level simulation. So in red, we have the Shannon bounds. So actually those are obtained from the optimization with locked 1 plus SNR. This is RSMA, this is SDMA. So we have a very significant gain there. But this gain is actually further amplified when you go to the link level. You see that actually this is RSMA link level, and this is SDMA link level. And so here, if you want to achieve 1 bits per second per hertz of throughput, you need 120 watts per antenna power at the feed, while you would use even less than 20 watt with rate splitting. You would probably be here to achieve just 1 bit per second per hertz. So you can imagine the huge savings in terms of power that you can get by using rate splitting here. And so this is actually very encouraging results. So to conclude, rate splitting relies on partially decoding interference and partially treating interference as nodes that enables you to bridge these fully treated interference as nodes and fully decoded interference. It's robust. You can view this as a robust interference management strategy because it's robust in perfect CSIT. It's flexible because it's flexible to any interference level you have in the network. It's general and unified because you can relate to SDMA, OMA, and NOMA as sub-strategies of that framework. So there is less benefit in looking at all different multiple access. You have just one of them. And in some instances, it can happen that actually the RSMA strategy boils down to given schemes. And it leads to some change in the physical layer and the MAC layer of communication strategies, of communication systems. Terrestrial, satellite, other systems. And so in terms of performance benefit, I have highlighted here spectral efficiency gains. You can have also energy efficiency gains. There is a quality of service and fairness enhancement, this robustness to imperfect knowledge of the CSI. It's suited to satellite settings because of the network load that can be very much towards the overloaded regime. Because you can have a variety of user distributions. It can be channel direction, channel strength, and it could be network load in terms of having asymmetric distribution of users in different beams. And you can have a complexity reduction that can be quite significant. I have not emphasized this here. This is something I talk about in other talks. But in some of the results here, we had NOMA results, for instance, here, right? So you have here, for instance, I've not emphasized, but you have NOMA results here that perform quite poorly compared to the SDMA and the rate splitting, simply because you're not in a good regime here to fully decode interference. You force yourself to fully decode interference, while maybe it's actually not a good regime to actually do it. And that's the reason why you can have significant performance loss, despite the fact that you can have higher, even though you have a higher complexity at the receiver, because you may have multiple SLs. So this is something you can look into other references if you're interested. So things that we're looking at is currently we have a project with the European Space Agency where we're doing a rate splitting for dual functional radar and communication. So this is something we have looked at for terrestrial network only, but it turns out that actually when you have integrated, when you have satellite systems, the joint radar and communication can really leverage rate splitting architecture as well. You can look at rate splitting for UAV, high altitude platform. You can have very mobile satellite systems also, or LEO satellites, something that has not been looked at. And rate splitting really leads to fundamental, really a broad range of new research problems on the fundamental limits on one hand, on different communication techniques for different scenarios, for different communication systems, the satellite, terrestrial, integrated networks, and you can have lots of issue more on the implementation, the standardization side as well. And so if you're interested, I encourage you to have a look at this special interest group that we have on RSMA, and where 1J is also actively contributing. We have best readings there that I encourage you to have a look at. We have lots of tutorials, and we organize events and talks on a regular basis. I think last one was Rodrigo de la Mare. We had Robert Schober 2 weeks ago. So next one, we're going to have Wolfgang Utschik from TU Munich. So we have lots of ongoing talks. And with this, I will conclude here, and we'll be happy to answer any questions that you may have.
Okay, thank you, Bruno. Yeah, it was a very nice talk. So I think, yeah, there are some questions from audience. So if there are any questions, feel free to ask to Bruno. Okay, Juan, go ahead.
Yes. Hi. Thank you for your wonderful presentation, Professor. I think the Doppler effect is not be considered in this presentation. I think so.
Sorry, which effect?
Doppler effect.
Doppler.
Yes.
No, we don't have Doppler because we assume geosatellites.
Yeah, that's right. I think it will be considered in your future works, that is in LEO satellite communication. So in my question, can we add the mitigation of Doppler effect in this RSMA technique? There is right. Mitigation
so
of yes.
I think in LEO, yeah, Doppler needs to be considered because the speed of the LEO satellite is really huge. So it's something we have not looked at. I mean, obviously, the Doppler will have issues on all the synchronization on one hand, and also it will have issues, further issues on the whole CSI feedback. The latency may be a bit reduced compared to GEO, but because of the speed that is so high, you can have quite significant change in the CSI. So something we have not looked at. We have looked at the problem of mobility. We have looked at for terrestrial network, where we compare rate splitting. We design rate splitting for mobile conditions, and we show that rate splitting enables to maintain multi-user connectivity over conventional multi-user MIMO at much higher speed. This is something we have shown, and we have papers on that. And so I suspect that similar results will happen in the LEO case as well. But specifically on the Doppler side, modeling the Doppler on the synchronization, for instance, that's not something that we have looked at. So we have not really investigated this. But that would be obviously, I think, quite important.
Yeah, in fact, Juan and I is working on that side. So with emphasis on the Doppler effect comes from the LEO. So
makes sense.
Yeah, I hope we can have some initial results and discuss with you.
Yeah, I mean, sure. I think, I mean, feel free to, we can meet face to face since we're neighbors, especially if you want.
Thank you.
Any other question? Yeah, I think the master can have one question. He's also working on this topic.
Hello, Professor. Thanks so much for your nice presentation. I think this presentation will be a very good presentation for us to proceed on our research on satellite communication. RSMA, and I understand that you mentioned about non-orthogonal multiple access. I think any more non-orthogonal multiple access will not be applied in the future communication systems, right? Is it possible the industry?
I mean, we don't know. I mean, my opinion about NORMA, and when I say NORMA, is power domain NORMAs, which is coding with SIC. I'm not referring to other forms of NORMA, code domain NORMA, and so on. I mean, I think this is a good scheme when you have single antenna networks. This is well understood for quite a long time, if you can afford the complexity increase. But my personal opinion actually is not a good scheme for when you do multi-antenna. So I don't think that's actually, I don't see this as a promising schemes for multi-antenna setting, which is prevalent nowadays. All systems are multi-antenna. So, and the reason for this is that if you're interested in this, you can have a look at this paper. We explain really why there is an issue there. Is really the fact that essentially you can have other strategies. I mean, you lose in terms of multiplexing gain, and at the same time you increase your receiver complexity. And what the least you would expect from a more complex schemes is to have at least a higher performance. And here you can have a loss of multiplexing gain. So you can have a loss compared to SDMA. While rate splitting, you never have a loss compared to SDMA. The worst you can have is at least is to have the performance of SDMA, but you will never have a performance worse than SDMA. So the way the SIC is used is quite different from the NORMA, because you don't force yourself to be in a decode interference regime. So that's my personal opinion about this. But we never know. I mean, you know, between what academia does and what industry does, it can be quite different.
I agree with you, Professor. So because during my PhD, I heard that, and I also recognized these issues on my research, and also conducted studies in the literature. And also I heard that from my professors in Turkey and other countries, that industry is not willing to apply this non-orthogonal multiple access in the future. Actually soon, maybe it should be some disadvantage of the non-orthogonal multiple access should be overcome somehow. So in this point, I think RSMA is really good technique. So I have never investigated RSMA, but we will study on it with Professor Shin. So I actually want to ask that what do you think about using airplanes for communication between satellite, MEO, LEO, and airplanes and terrestrial? What do you think about using airplanes as a it can be an relaying procedure, maybe relaying structure, similar to hubs, maybe considering hubs.
Yeah, I mean, I don't have a strong view on that, because I mean, yes, I think there's some people who have looked at that a little bit. I know Laios Hanzo in Southampton has been advertising the use of interplane communication as a way to relay information. For instance, if you want to communicate between Europe and, I don't know, between London and Seoul, for instance, you could transmit data directly to a plane. The plane would relay this to another plane and another plane, and so on. And and the plane could be connected to satellite as well. I think it's really possible. Yeah. I mean, this is a more deployment scenario. I mean, I think all those scenarios are possible. I don't know what industry people would feel about this. And in all those scenarios, I mean, I think potentially some of those techniques I talked about today could be beneficial. It all depends on, in general, all those gains depends on the deployment scenario, the objective functions, the quality of the CSI, the number of users, whether you are more in the overloaded regime or underloaded, and whether you really want to have quality of constraints and fairness, and take into account fairness into the problem. The more you have fairness constraint, the more gains of the more you have gains from rate splitting. But I think the scenario you mentioned, yeah, I think it's possible. It's not something I have a strong view about. Maybe industry people would actually know more about that.
Yeah, thank you so much, Professor. Thanks so much.
So I have one quick question. So maybe can you go back to page 26 or something? Any like simulation result? Yeah, here. So it seems that all the rate curve are saturated as the per antenna power is increased. Is that because of the number of antenna is not enough to cancel all the integer interference?
So it saturates. I don't think so. Here, this one is the multi-gateway. It does not saturate. I think with rate splitting, it keeps increasing.
Yeah, I also expect that, but
yeah. Let me see the other figure. You see here, it does not saturate. I mean, as you increase the per antenna feeds, here it does not saturate either. I mean, some scheme may look like saturating, maybe because of the way the interference is managed. Maybe like the NOMA here seems to saturate much more than the RSMA. Yeah, so you see here it's increasing.
Yeah.
I have to look.
In this case, maybe we can.
Saturate.
In this case, we can also consider just a multicast scenario. I mean, multicast transmission. Over a message can be sent out in a sense of the multicast. Then it avoid the saturation, right? But
I mean, you can do multicast, but I mean, the problem of multicast, we have this in some other works, is I mean, multicast is not always good, right? Here you have beams, and so you want to make use of those beams because you have some interbeam interference, but it's not like you have a trade-off between doing multicast on one hand, doing unicast on the other hand. And your rate splitting is actually something in between in a way, because some of the bits transmit common stream, which is a bit reminiscent of a multicast. I mean, physically speaking, it's like a multicast transmission because it's encoded by all. And this multicast transmission is what avoids any form, eliminates any form of saturation. So that's why rate splitting usually, I mean, I've never seen rate splitting saturating per se, because your SINR of the private streams could be interference limited, but the common streams, the rate of the common stream will not saturate. The SINR of the common stream does not saturate because it's decoded by all. But here you have to keep in mind on those figures, this is not in dB scales, right? So when you go from 100 to 120,
you do not linear scale.
It's linear scale. So you do not increase by 3 dB or so. That's the reason why also maybe it's quite small. would be interesting to look at in the dB scales. Right, so I think this is what I think is happening.
Yeah.
Okay.
Yeah. Okay.
I will have to leave you now because I have a call at 6.
Oh, okay. Yeah.
But
Okay.
yeah, feel free to let me know if you have more questions by
Okay.
email or at some points.
Okay. Thank you, Bruno. Yeah. It's
and hope that was helpful. I can send you the slides as well.
Okay.
And that's it. Keep in
Okay.
touch.
Thank you.